My name is Jean-Paul Vella, and I am going to talk about our paper on the investigation of headed bar joints between precast concrete panels. It is common in precast concrete construction to use in situ concrete joints to connect separate precast panels together. The research presented in this paper shows that a 100 mm long lap in 28 MPa cylinder strength concrete is sufficient to develop a full strength tension lap of 25 mm bars compared with over a meter for straight bars. The use of such headed bar joints facilitates precast concrete construction, which has the benefit of allowing a large proportion of the structure to be fabricated off-site. This reduces site labor whilst achieving significant improvements in quality, reduction in construction waste, and shortening of construction programs. The floor system presented in this paper consists of precast slabs with projecting headed bars lapped together in a 200 mm wide joint. Additional confining reinforcement is installed on-site in the form of transverse bars and out-of-plane shear studs. This joint has many practical applications and is used by Lango Work in their patented E6 floor system. Results are presented from 27 tests on 3-bar tension splices, which are intended to represent the tensile zone of a slab subjected to flexure. The adopted headed bars were 25 mm in diameter, having a yield strength of 260 kN. The tests studied the influences of concrete strength, transverse reinforcement, confining shear studs, headed bar spacing, and splice length on joint strength. Reinforcement forces were derived at different locations from strain gauge readings. Digital image correlation was used to capture three-dimensional displacements, strains, and crack propagation on the surface of each specimen. Results show that joint strength increases with concrete strength and provision of out-of-plane shear studs. Joint strength also increases when transverse bar diameter is increased from 16 mm to 20 mm, but no further increase in strength was observed with 25 mm transverse bars. Transverse bar arrangement was found to affect joint strength significantly. Higher joint strengths were achieved when the bar arrangement was changed from 2 bars top to 1 bar top and 1 bar bottom. Even greater joint strengths were obtained with 4 transverse bars. Joint strength also increased with increasing lap length and decreasing headed bar spacing. The paper presents a strut and tie model and an upper bound plasticity model for predicting joint strength. The strut and tie model gives conservative predictions of joint strength, while the upper bound plasticity model gives greater but reasonable estimates, with some scatter. Both models do not fully capture the complex behavior within the joint. Future research will look into nonlinear finite element analysis of these joints and at their visibility limit state behavior by means of flexural slab tests. The main conclusions from these tests are as follows. Joint strength and ductility is significantly enhanced by placing transverse bars on both sides of the headed bars rather than on one side. A lap of 100 mm in concrete with 28 MPa cylinder strength was sufficient to develop the full strength of the headed bars when providing 4 transverse bars. Increasing concrete strength increases lap strength when governed by concrete failure and can change the failure mode to headed bar yield. Providing shear stud in the lap zone can increase joint strength and ductility. Joint strength and ductility is also increased by increasing lap length or reducing headed bar spacing. The understanding of headed bar splice behavior achieved through this research will help inform the development of alternative design approaches and facilitate the optimization of joint design. Thank you for your interest in our work, and please feel free to share this presentation with any colleagues who might also be interested in this research.